This video is going to look at diagonalising matrices, what that means, how we can use eigenvalues and eigenvectors in order to do it, and then how we can apply this to find higher powers of matrices without doing a whole load of calculation. So this video isn't going to prove the result I'm about to claim. If you want that, there should be a video coming soon if you're interested in that, but it will be focused on the application. So when we're talking about diagonalizing a matrix, what we mean is taking a matrix M and writing it as the product of three matrices where we've got the matrix P and its inverse on the left and right, and a purely diagonal matrix in the center. By a diagonal matrix, we mean a matrix where all the entries, except for those on the downward right diagonal, are zero. So these aren't zero and the rest are. Now, in order to do this, the result we're going to use is this matrix P is going to consist of all the eigenvectors of the matrix. Now, in this case, I've written it as though we've only got two, but if we've got a 3x3 matrix and three eigenvectors, it would just be v1, v2, v3. And your diagonal matrix D is going to consist of the corresponding eigenvalues, lambda 1, lambda 2, and if you use 3x3, lambda 3, and all the other entries are going to be 0. Note, you need to make sure that your v1 and lambda 1 match up and go in that order. If you write your matrix P with your eigenvectors the other way around, the result will still work as long as you put your eigenvalues the other way around for D as well. So we're going to do an example, and then we're going to look at how we can use this example to do higher powers of matrices in a slightly quicker way. So the example I want to look at, I'm going to give you just a 2x2 matrix to save all the hassle that comes with looking at 3x3 eigenvectors. And I'm going to tell you that M is equal to matrix 1, 3, 2, 2. And the first thing we want to do, whenever we're trying to do this, we're trying to find P and D. So we want to find the eigenvalues and the eigenvectors. So we'll start off with a reminder how to do that. To get the eigenvalues, we're going to start by saying we want the determinant of M subtract lambda I to be equal to 0. We're looking for the values of lambda which make this work. Now, M subtract lambda I is just the matrix 1 subtract lambda, 3, 2, 2 subtract lambda. So the determinant of that, because it's 2x2, this is fairly easy for us at the moment. So we're just going to do AD, or 1 subtract lambda times 2 subtract lambda, subtract BC, which is just subtract 3 times 2, which is 6, equals 0, expand, so we'll get lambda squared, we'll get subtract 3 lambda, and plus 2, subtract 6 equals 0. We've got a quadratic, which we're hoping for, because we're expecting two eigenvalues. Subtract 3 lambda, subtract 4 equals 0. And then no problem, we can factorize lambda subtract 4, lambda plus 1 equals 0. And we'll get two eigenvalues. I'm going to call them lambda 1 and lambda 2, just so I can make clear what we're doing at each stage. So lambda 1 is equal to 4, lambda 2, my other eigenvalue is negative 1. If you label it the other way around, that's fine. Just be consistent with your labeling when we get to the eigenvectors. So for each of these, we now need to get eigenvectors that go with them. So let's consider lambda 1 equals 4 first. So for our eigenvalue, lambda 1 equals 4, how are we going to find the eigenvector? Well, we're always trying to solve the equation m subtract lambda I is equal to 0. Well, is equal to 0. Oh, sorry. M subtract lambda I times by v is equal to the 0 vector for our value of lambda. Now, fortunately, m subtract lambda I, that's nice and easy. We're just going to sub in 4 into the matrix we just did when we had m subtract lambda I. So that's going to give us negative 3, 3, 2, and negative 2. V, because it's a 2x2 vector, sorry, a two-dimensional vector, we're just going to say it's xy is equal to 0. And now if we expand, we'll get two equations, but we'll see they're really the same equation. Negative 3x plus 3y is equal to 0. 2x minus 2y is equal to 0. Both of these equations are really just y equals x. So any vector that's in the direction of that line will work, that satisfies that relationship will work. So the simplest one we can choose is just the vector 1, 1. I've just lost my pen a second here. 1, 1. There we go. So we've got one vector. Let's do the other one now using the similar method here. In fact, you can check that yourself. I'm just going to tell you what you're going to get here. if we do lambda 2 equals -1 and repeat that trick, you should end up, after a little bit of work, you should get that you have 2x plus 3y equals 0 coming out as your equation. If you rearrange this, you can see this is y equals -2/3 x, and a vector in that direction. If you want all integers, you can go for 3, -2. If you pick x equals 3, it gives you y is -2. Any multiple of that would work and we'll be fine. We're just going to pick one now because we've got infinitely many possibilities. So now we've got that. Going up and using the results that we had, well, we can now say what our matrix P is and what our matrix D is. So in this case, we can say the matrix P is just going to be equal to the matrix consisting of our two eigenvectors. So 1, 1 is our first eigenvector, 3, -2 is our second eigenvector, and then our matrix D has diagonals of our eigenvalues, 4, -1, and the others are zeros here. So those are our P and our D, and our matrix, we know from our result that's P times D times P inverse. Now, what's the use of this? It seems a bit of a weird thing to want to do. Well, the value of this is, let's say I want to find m to some power. I'm not going to choose too high a power here just because the numbers get really big. But if we wanted to do big powers, this would be a much more efficient way than anything else. I'm just going to say, can we use this idea to find m to the power of 4? Obviously, we could just do m times n times n times m, but let's try and exploit this because we'll be able to exploit it with high numbers. So if we do this, now this is P, I'm going to give up underlining here because there's too much underlining, but P times D times P inverse times P times D times P inverse times P times D times P inverse and times P times D times P inverse. Now, I've not written brackets here because matrix multiplication is associative. It doesn't matter why you put the brackets. And for that reason, we can do the multiplication in any order. And let's look at what we've got here then. This P inverse times P is just going to be the identity matrix. Same again, that was a P. P inverse times P and P inverse times P. So they're all going to disappear. And all we're going to be left with is P times, we're going to have D here, D here, D there, D there, and D there. So D times by itself 4 times, so D to the 4 times P inverse. Now this might look not that much nicer. It's a much easier matrix multiplication to carry out here. So let's put in what our matrices are. We've got P, which is 1, 3, 1, -2. We've got D to the power 4, which is this to the power 4. And then we've got P inverse now. Finding the inverse of a 2 by 2 matrix, not too bad. If you're being asked to do this, you can definitely use a calculator to check anyway, because on a 3 by 3, it's going to be a bit nastier, but you can definitely use your calculator to speed you up there. And then finally, our inverse matrix, well, finding the inverse of a 2 by 2, it's going to be 1 over the determinant. Our determinant is -5. So it's going to be 1 over -5 on -5. And then we're going to swap our top left and bottom right entries and negate the other two entries. And now we've just got a big matrix multiplication to do. Now, why is this any more useful? Because we've still got a power 4. The reason it's useful is because this matrix to the power 4, if we've got a diagonal matrix, is just each of our entries to the power 4. So 4 to the 4 is 2, 5, 6. -1 to the 4 is 1. And no stay 0. The rest we've still got to deal with. I'm going to pull the -1/5 to the front just because that's looking a bit untidy there, but you don't have to do that. That's completely up to you. We've then got 1, 3, 1, -2, and we've got -2, -3, -1, 1. At this point, we do just have to go through and do some matrix multiplication. There's no really super quick way of speeding ourselves up here, but if I'd given you m to the 100, we've saved a lot of time here. Like I say, I'm just going for this to stay dealing with more reasonable numbers. So here, you just want to multiply those first two matrices together. I'd keep the -1/5 outside for now. And that's going to give you 2, 5, 6, 3, 2, 5, 6, -2, times by -2, -3, -1 and 1. And then you can do the next multiplication. Again, nothing fancy going on here. -515, -765, negative 510, and negative 770. And now finally, everything's divisible by 5, so it makes sense to put a negative fifth back in, and we end up with our answer of 103, 153, 102, and 154. So whenever the key idea here, though, comes at this step here, where when we write it out, all our p's and our p inverses in the middle cancel, and m to the 4 is just going to be p times d to the 4 times p inverse. If we're doing m to the 100, again, we'd only have 1p and 1p inverse, and we'd have d to the 100 here. Much quicker way of going about that. Thank you very much.